Data structure using C++, module 5, session 9. So we were discussing about how to delete a node from a binary search tree. So in this session, we had assumed three possible cases for deleting a node from a binary search tree. That is, P is a leaf, P has exactly one non-empty subtree, and also P has exactly two empty subtree. So these two possible cases we have discussed. Now let's see what if the node which we are supposed to delete is having two children's. So now let's assume this is the structure. This is the structure, and here in this binary search tree, say that the key which you are going to search is 30, and that node with this value needs to be deleted. And in that case, which is actually the best value which will be replaced by this, you need to figure out. And you have two options. The first option is either you can select the largest element in the left subtree, which means 5 can get replaced over here, or you can either select the smallest element in the right subtree. So this would be the right subtree of this node 30. So the smallest element in the right subtree is 31. So 31 can be replaced over here. So by doing this too, definitely the binary search tree after deleting a node will remain as a binary search tree. Now let's discuss this code. So basically what you are trying to do is we create a node, and since we are interested with the left subtree element, so we will be finding the largest element in the left subtree. That is done with the help of a pointer named q, and largest element in the left subtree will be put on the pointer q with the help of an instruction new. So we can create a pointer q, and we can also make use of a new instruction. Doing so, we can add an element there, and after that the structure would look like this, and later we create one more pointer, and in this case we make the pointer c point to the child of the previous pointer. So this would be the situation. Finally what we do is we just make sure that rather than pointing pp will be pointing to the root node, and this element would be replaced by 5 value, and later rather than making pp point to p, we make pp point to c. Okay, so pp of left child, rather than making it point to p, we make it point to c, and later we can delete the pointer which was pointing here using delete p, so that will be destroyed. Now let's look at the program, how this is achieved with the help of a program. Now the key value, we will assume it is to be 30. 30 is the value, and that's the root value, and that needs to be deleted. So this is your program. The key is 30. So we have to figure whether this is having two children or not. So how it is going to get checked? So first it creates two pointers. P would be pointing to the root, and pp is equal to null. So this is pretty much clear. Then we have instruction why p not equal to null. So p is not equal to null, and p element dot first not equal to the key. Now what is the case? The key value is 30, and element dot first. So when you observe this structure, element dot first, this is your node, and element dot first is 30 itself. So that's matching. So in this case, you are supposed to break the while loop. So the while loop, which was over here, would be broken, and still p will be pointing to root, and pp is indeed null. Okay, so this piece of code will not be executed. So you come back over here and you check whether the condition p is equal to null satisfies. So right now p is having information, so that's not null, so it doesn't return, which means you are supposed to proceed with. Now let's look at what is gonna happen right now. Now we have p left child. So when you observe this structure, this is having a left child as well as it's having a right child. So in this case, this code will be executed. This code will be executed. So this will execute if the node which is under consideration is having two children. Now p of left child is not null, and p of right child is also not null, which means this is having two children. So what you have to do, you have to find the largest element in the left subtree. For that, this is the procedure which you need to follow. So first what we do is we create a node pointer named as, and that's pointing to where p of left child points. So now let's look at this. This is where the p points. So where does p of left child points? P of left child is pointing over here, right? So this is where p of left child points. So when you look at this structure, second structure, you can see there is a pointer named S and it's pointing where P of left child points, right? So this is okay. So hope this is clear. It makes sense. So S is the pointer and it is pointing to P of left child. So that's done with the help of the command this, right? And after this we create parent to S and that is pointing where P points. So now when you look at the structure, P is pointing here and we create a node PS and that's pointing where P points. So this is the structure. So this pointer is also created. So PS is created, S is created. So what is PS? PS is parent of S, and what is this? S is a node which is a left child of your parent root, which means that is having a maximum value which should be replaced now. Okay, next moving on. So what we do, we check this condition: is S right child not equal to null? So when you observe this is S and this is having left child but not right child, right? This pointer is having a value node value phi and it's having a left child but no right child. So this while condition which we are looking at, okay, so this is the while condition which we are looking at. This condition is false. That's equal to null. S of right child is exactly equal to null. So this will not be executed, right? Okay, so in that case what you have to do is move largest from S to P, right? So you just observe this figure. The P is having the largest element. So what you have in S, this is your largest element. So this has to be moved to this position. So that movement is done with the help of the next code. So for that we create a new node named Q. Okay, then we will insert the value in there which is equal to the value present in the node S. That needs to be done. Then what we can do, make Q point to the left P of left child and also make Q right child point to where P of left child is pointing. So do that, then ultimately this structure comes, right? So now you can say that Q of left child is pointing here, right child is pointing here, and Q of left child is pointing here. Okay, then you can completely delete this node. So in that case this is how the structure looks like. Okay, so let's see how it is done here. So so we were over here. So this was actually which I was talking about. So what we do is we create a node pointer named Q. So after doing this, using instruction new, we use binary tree node pair, and for this node pair, element left child and right child explicitly we define. So for this Q node, the element which we are supposed to insert is the element which you are having at S element. So what is there in S element? So this is your S element present where S points is phi. So phi should be inserted for the pointer Q. Okay, so phi is inserted here, and next instruction what we do is we make sure that the left child over here, the left child of the Q pointer is pointing to where P of left child points to, and also its right child is P of right child. So we create a node with three components: node, right child and left child. So now what happens after adding this or after writing this code, the structure looks like this. So we had created a Q and its left child is pointing where P of left child is pointing. This was a position for P. P of left child points here, which is S itself position, and Q of left child will also point to the same node. Okay, and the P of right child is pointing here, and we make sure that Q of right child is also pointing there. So this will be the structure. So now you can see that there are two nodes which is pointing to the phi and 40, that is Q as well as P, both are pointing. Now we can delete P, and once it is deleted, this link will be broken and we can get the structure something like this. And also the P which was pointing here, it has to be redesigned. So P has to be changed. So P should go here. P should go here because this element we need to delete, so which is there over here. See, we will see how it is done. Okay, so hope this much is clear. So what we do, we create a node, add S element, P left child and right child. Now we check the condition, is PP is equal to null. So which means right now this is the scenario here, PP is null, right? PP is null, correct? So in that case, which means the element which you are going to delete is root itself, correct? So what we do is we write root is equal to q. So q becomes the root. That's true, which means this else if will not be executed, even else will not be executed. Then we directly move on to this instruction. Okay, so now the situation is we make pp is equal to q. Okay, so pp is equal to q. So this is where pp points. Okay, so we'll see how it is done. So here we write pp, yeah, this is done. So this much is not executed. Now we check whether ps is equal to p. Is ps is equal to p? So when you look at ps parent to s, which was pointed here, and p is also pointing to the same node. So ps is equal to x, that statement is true. So in that case, what we do is we set pp is equal to q. It should be done. So it's done here. So we write if ps is equal to p, then pp is made q. So pp becomes the parent of p now, and that's q pointer. Okay, so after writing this code, we get the structure like this now. So pp points here, pp points here, and p is here. Okay, now what you have to do, delete this p and make this as p, replace s as p, so that this becomes the new binary search tree. Then we have to ultimately delete this one. Let's see that. So right now we are down the line here. So this much is done, pp is equal to q. So else condition is not executed. We delete the p, we delete the root, and we set p is equal to s. So by doing this, we get this structure. Okay, so we, this was the p which was pointing, so we destroyed this link. So the t goes, this is completely destroyed, and ps is also not there now. Now you get a tree structure like this. Okay, just consider this structure, don't consider this structure. So you'll get this as the restructure of the binary search tree. Now we have p, and yeah, p was here, correct? Now p is not here yet, p is it here. So what we have to do, make p point where s is pointing. So s is pointing, make that there, the p is pointing. So p is pointing here now. So s is also pointing to the same node, which is 5. So it is not indicated, but still it points here. So now this is your structure. Okay, after processing this whole piece of code, you'll be getting this structure. Now let's see how from this structure you are going to this structure, because this is your ultimate result which we expect. So now here only one thing, that is this has a redundant information, this should be deleted, and this has to be connected to this node. So to do that, we create a new node C, and this code was already explained. This is a case wherein we assume that a node which we are supposed to delete is having a one child. So when you observe this structure, this is actually the node which we want to delete. This is having a one child. So let's this is already discussed. Again, we will discuss how this brings the structure again. Okay, so here we create a node C, and doing that you get C is pointing to this node. How it points? So because we create a pointer, then we will check if p of left child is not equal to null. So right now here p of left child is this, and it's not null. So what you have to do, we make sure that where p of left child points, there let C point. Okay, that is done with the help of this instruction. C is pointing to where p of left child points. So p of left child is pointing here, so C will also point to the same node. So you have two nodes pointing to this 2. Okay, after that what you have to do is you have to delete this p, and you have to the pp of left child should point to C rather than right now it is pointing to p. Rather make it point to C. That's the final stuff. Okay, so this is done now. Okay, then what we do, we check if p is equal to root. Right now p is not a root, p is not in the root, it's the child of the root, right? So this will not be executed, and we check this else condition will be executed, and here we check is if p is equal to pp of left child. When you observe this structure, p is pointing here and pp of left child is pointing to the same node, which means this condition is true. So if that condition meets, then what you have to do, pp of left child, make pp of left child point where C is pointing, right? So pp of left child right now it is pointing here, make it point where C points. So This will be the structure. Okay, this will be the structure. It is shown here, and then you delete where p points. P is pointing here. Delete this node using the instruction delete, and also decrement the tree size. So tree size is decremented. So one element is destroyed. Finally, we use instruction delete p. So this is the execution. The complexity, I know that this program is very much complex. In your exam, if at all the question is posed to ensure that how the element gets deleted from a binary search tree, you can just talk about the method. You just talk about the method rather than explaining the code. Okay, don't go to explain the code, because the program is not important here, because you have a huge set of lines coming into play. So probably you can, just understand the concept. Three possible cases you can explain with the help of a structure. Always try to explain the program. Okay, program is not important. I mean, just take one binary search tree, indicate how actually a node gets deleted, if it's a no, if it's a leaf node, if it's having one child, or if it's having two child. So that's better rather than writing this piece of code and not explaining it. Okay, so this completes module 5. The last topic, which I'll just tell you what basically this means. So you have binary search tree with duplicates, and for that program to make it work, in the insert program, almost all other program remain same. Insert program, this line will be replaced with this piece of code. So first of all, I'll talk what is binary search tree with duplicates. So we know what is binary search tree. In binary search tree, we talked about a binary search tree will have all keys unique, whereas for duplicates, a key could be equal to. Okay, which means the key can be repeated, or it can be duplicate values. You can have same key with many nodes can have same key value. That's possible. So you call it as binary search tree with the duplicates. The key information may not be distinct here, it could be different. So that's why you call it as binary search tree with duplicates. So what we do basically here is, rather than using this condition, insert program the pair dot first less than condition rather than less than, because now you can have this case also, because the first value can also be equal to, okay, the element which you want to insert. Okay, that could be equal to the first pair can also be equal to pp of element dot first. So this is also not that important. So if you want to work on this, you can definitely try. What basically happens when we talk about binary search tree with the duplicates, just replace this line, one line, with this set of code, and see how this behaves for different insert function. You can consider one simple example of inserting key value. Say assume that 50 you have here. Yeah, this is insert program. You can take this simple example, and you can think as if 50 is also there over here. Okay, you can take 50 here, fine, or you can take 20 and 20, just to make it easy, more easy, take 20, this again you take 20. So two keys are having two keys are same, so that becomes binary search tree with duplicate. So in that case, how the program works, if the key value is also 20, in that case how this works, that you can think and you can just try to work with this program. Okay, so this completes module 5. Thanks for watching the video.